Hey there, in this video we are going to look at how the three primary trig ratios are defined for any angle in standard position using the coordinates xy of a point on the terminal arm of that angle, and then look at what that means in terms of the trig ratios being positive or negative in each of the quadrants. As you probably know, the classical definition of trig ratios has to do with sides in a right angle triangle, which you usually label or look at as opposite, adjacent, and hypotenuse in relation to this angle there. And as you change that angle, the ratios for sine, cosine, and tangent change as the side lengths change. And this definition works well for angles in right triangles that go from 0, even though that's not really a triangle anymore, just kind of two sticks, all the way up to 90 up here, which again is not a triangle. But aside from that, this definition works well for angles between 0 and 90. But what if we want to work with angles that are bigger than 90? Angles bigger than 90 can't be in a right triangle, because if you think about it, you have this right angle down here, that's 90. That only leaves 90 degrees for the other two angles. So if you have an angle bigger than 90, it can't be part of a right triangle. So this classical definition of trig ratios isn't going to work. So what do we do then? Well, what we do is we don't think about our angle as being in a triangle. We put it in standard position on a set of axes. And so say if we have an angle of about 60 degrees, instead of just drawing a triangle like that, we're going to think about it as being in standard position. So we have that terminal arm there, and then we have our initial arm here. And then what we can do is use any point that's on this terminal arm, the coordinates of that point, xy, and we can use that to define our trig ratios for this angle here. This is theta. Now, just like before, we're going to look at this triangle like that, and instead of thinking of opposite, adjacent, and hypotenuse, we're going to realize that this distance right here is the y-coordinate, this value right here. And we're going to realize that this distance right here is the x-coordinate. And then this distance that, in a triangle we would have called the hypotenuse, what we're going to do is we're going to call it r for radius, because we're going to imagine that this point can rotate all the way around here like this. So it traces at a circle if you rotate it around. So we have x, y, and r. And we're going to write our trig ratios based on that. Now, if you just look at this little triangle here, for the sine ratio, we would have defined it before as, from this angle, we would have defined it as the opposite over the hypotenuse. So in this case, what we're going to do is define it as y divided by r, the y-coordinate divided by the radius. And we're going to do the same for cosine. Cosine of that we would have defined as adjacent over hypotenuse, but in this case we're going to define it as x over r. And lastly, for tangent of that angle we would have defined it as opposite over adjacent if we're looking at that triangle. So in this case we're going to define it as y over x. Now you might say, what's the difference there, whether you call it opposite, adjacent, hypotenuse, or x, y, and r? The good thing here is that if we define this way, then we're not tied down to this angle being in a triangle, because as soon as we rotate it over to there, we can just use the same definition. So let's say this angle was over here, something like that, and then our point is going to be over there. So point on the terminal arm somewhere, and we have coordinates of that point, still x, y. We can still use these same definitions. Even though this angle theta is not in a triangle anymore, we can still use that same definition. And in fact, we can still kind of look at this triangle here that this makes with the x-axis, this what you call a little reference triangle, and we can think that's the y-coordinate, that's the x-coordinate, and then we have r. Those definitions still hold. You can use them in any quadrant. Now, as much as my rough sketch here kind of gets the idea across, I have something a little bit more dynamic for you that'll illustrate it far better. So in moving from using sides of a triangle to define the trig ratios to using coordinates of a point on the terminal arm, we can now have trig ratios defined for any angle regardless of where it is. So not just angles between 0 and 90 that are in quadrant 1, but any angle. You move over here to quadrant 2, you have angles between 90 and 180. Trig ratios are still defined over there. Into quadrant 3, same thing. Into quadrant 4, same thing. Now, what you might notice that is significant here is as soon as you cross into any of the other quadrants, you notice that some of the trig ratios are now negative. And if you think about the definitions that we wrote, the y over r, x over r, and y over x, it makes sense. In quadrant 2 here, the sine is a positive number. Sine in our circular definition here is y over r. Y is a positive, this y coordinate's positive here, and r is a distance out to there. It's always positive. When you divide those two things, you have a positive number. Whereas the other two here involve x. Cosine is x over r. In this second quadrant here, x is a negative number. So when you have a negative number divided by this positive radius, you get a negative ratio. And the same goes for tangent. You have y divided by x. Y is a positive, x is a negative. If you divide those two things, you get a negative. So as we move out of quadrant 1 into the other quadrants, some of the ratios are going to be negative. When you go into quadrant 3, if you think about it here, now tangent's the one that's positive, and the other two are negative. Tangent is positive because we have the y coordinate divided by the x coordinate. Both of those are negative here, but when you divide them, that gives you a positive number. So tangent's positive in quadrant 3. The other two are negative because they only involve one of these and the radius. Sine is y over r, negative divided by positive, and cosine's x over r, negative divided by positive. So both of those two are negative there. And then into quadrant 4, you notice that two of them are negative as well, sine and tangent. Cosine's the positive one in quadrant 4. Cosine's positive because it's the x coordinate divided by this radius. X coordinate is positive, radius is positive, gives you a positive ratio. But the other two involve y, which is negative here, making them both negative. Sine is y over r, negative over positive, and tangent is y over x, negative over positive. So once we extend our definition to any angle, some of our trig ratios are going to be negative as we go around here. Something else that's worth noticing is for angles in each quadrant that have the same reference angle, let's stop somewhere like say right there, where those coordinates are whole numbers, that the angle is 36.9. The reference angle there is 36.9, quadrant 1. The sine, cosine, and tangent ratios 0.6, 0.8, 0.75. You can get them from those coordinates, right? For example, cosine is the x coordinate divided by the radius. 4 divided by the radius of that circle's 5. You get the 0.8 there. Now, if we flip this over into quadrant 2, to that point where you have the same reference angle, but theta itself is now, of course, bigger than 90, 143. If you divide all of those things, two of them are negative, as we just saw, but the number part, the absolute value of all of those ratios, is the same. This is still 0.6, 0.8, 0.75, just that these two are negative. And that's because this is like a reflection of that triangle over to this side. This little triangle kind of reflected from one side to the other. If we go into quadrant 3 with that same thing, let's stop right there, right where we have that kind of reference triangle down below there. Reference angle of 36.9, same reference angle. Of course, theta itself is all the way around. But those same values show up. It's just now sine and cosine are negative and tangent is positive. And then the fourth one over here, the fourth angle that's related to that reference angle, 36.9, that little blue angle in there, the reference angle. Theta itself, of course, is 323, all the way around to there. But those same values show up, 0.6, 0.8, 0.75. It's just that two of them are negative. Sine and tangent are negative, cosine's positive. So angles as you go around that have the same reference angle are going to have the same numbers show up here, the same, what you say, absolute value. Ignoring the negative signs, all those numbers are the same. Now it's probably worth summarizing here which quadrants each ratio is positive and which ones it's negative, because that's pretty important moving forward here. You can always relate it to the values at x and y and r. Now to start with, it's worth remembering that r is always positive, so you don't even have to worry about it all that much. In quadrant 1, x and y are both positive. In quadrant 2, y is still positive, but x is now negative. Right? As soon as you're to the left of that axis, x becomes negative. So as you go into quadrant 3, x is still negative because you're to the left, but now that you've gone below this axis, y is negative as well, right? And once you get to quadrant 4, now y is still negative, but x, once you cross back over to the right side, x is positive. And from our definitions, y over r for sine, x over r for cosine, and y over x from tangent, you just think about the values, right? All of them are positive in quadrant 1 because y, x, and r are all positive. So all of these are positive. You have a positive divided by a positive. Quadrant 2. Quadrant 2, sine was the one that's positive because y and r are the two that are positive there. Anything that involves x in quadrant 2 is going to be negative. Both of these involve x, so they're going to be negative. Quadrant 3. Quadrant 3, tangent was the one that was positive because both of those being negative divide to a positive number. But the other two, sine and cosine, that only have one of those things in it are going to be negative. So they're both negative there. And then in quadrant 4, cosine was the positive one because the x-coordinate is the positive one, and x divided by the radius, positive divided by positive. Whereas the other two that involve y, which is a negative number, are going to be negative. And you can always generate those values by just thinking about the values of the coordinates x and y as you go around. Sometimes people like to have a simpler way to remember it. Sometimes people just think about where it's positive and then just know it's negative everywhere else. So what some people do is they just remember that all of them are positive in quadrant 1, and sine is positive in quadrant 2, and tangent's positive in quadrant 3, and cosine's positive in quadrant 4, and then they just remember this sequence of letters. Some people even make up a little sentence to remember those letters. The most common one you hear is, all students take classes, because usually that's the definition of what a student is. You can decide to remember it however you want. All right, so that's a look at the definitions of the trig ratios of angles of any measure in standard position using the coordinates of a point on the terminal arm rather than sides of a triangle.